Okay, well now for something completely different, and I see I made things a little big. You can't see the title of this, but
oh, I see. Okay.
well, we'll work around it.
Yeah.
And you know, I can get creative and tell you about all the cool things that are happening on the outside of this slide. That's where all the good stuff is. But for something a little bit different, but kind of related to the last discussion that we had, talking about Austro-Alpine tektite layers and Bruns-Maruyama boundary and things like that. We're going to talk about paleomagnetism and really, in this case, the Holocene, short time interval. I like a time interval where I can date things well and try to get an understanding of what's going on to help us really understand some of the dynamics of the geomagnetic field, understand paleodynamics, understands hopefully something about Tephra layers and what their sources might be. But of course, those are probably helping us more than we're helping them. But hopefully it's always a good handshake. So we're going to talk about combining Holocene Paleomagnetic records with Tephra stratigraphies and radiocarbon dates to improve our understanding of paleo records in general. And this work is with a host of people, but including specifically Ann Jennings' work we've been doing in Iceland, and Mark Abbott on work we've been doing in, oh, thanks.
This will help boost off.
Yeah, sure. And Mark Abbott with work we've been doing in Eastern Oregon. Acknowledge a whole host of other people here, but you always got to call out your funding agencies of NSF, OCE, and EAR, some Canadian funding, some Icelandic funding for a lot of this work, plus people in a variety of different institutions, because I'm going to touch on a lot of different things here. So, okay, so for a little background, Earth kind of is a giant magnet. It's a way to look at it. We typically see these textbook diagrams of things with a bar magnet in the center, but I always think the Glatzmeyer-Roberts, and do we have a pointer here? Oh, thank you.
Just press that.
Oh, okay. Yeah, this works even better. Okay, so I always like this picture from Glatzmeyer-Roberts. It was the first self-reversing geodynamo model, and it kind of shows you, this would be sort of looking at the core here. So we're looking at the liquid outer core, and you can see the dynamics of the field is very complex. It's not something, you know, it's not a bar magnet. It's driven by fluid convection of liquid iron, you know, and it's generating here, so you have this outward flux coming from the southern hemisphere and inward flux down, generating a magnetic field that doesn't look exactly like what we expect for a geocentric axial dipole, which is what we'd see, where everything would be really symmetric. Here you would have your lowest intensity right at the equator, and it would smoothly move up. But if we look at it, there's a lot of dynamics. You see a lot of color in different areas. Low intensity here over the South Atlantic, a couple high intensity spots over North America and over Siberia. If you look at inclination, it's fairly subdued. It's somewhat systematic, but there are some big dips in it that show up, and declination is quite complex. So these sort of variations in the field are something we can take advantage of, and they're what give rise to paleomagnetic secular variation, and it is a stratigraphic dating tool. Of course, just to give us some more background on things, declination is the deviation from north in the horizontal plane, like our compass is. Inclination is the deviation from horizontal in the vertical plane. It's 90 at the poles, 0 at the equator, and then back again 90 at the North Pole. Okay, but Earth is a giant magnet. It's a magnet that changes. And this is just a recent diagram that came out from the SWARM expedition satellite, 3 sets of European satellites that went out. And this is measuring geomagnetic change over the last 6 months. And I would argue that this very systematic change of reducing intensity here in the Western Hemisphere and sort of growth in intensity here in Eastern Hemispheres is something that's not just 6 months long, but is probably part of a larger scale process that may have a much longer time constant and is really key to a lot of geomagnetic change. There's a lot of evidence that suggests that these sort of oscillations are kind of what takes place a lot into the past. And it's this dynamic feature and these dynamic changes that we're really interested in and can take advantage of. And magnetic stratigraphy, as we know it, is based on these things. It's really based on the Paleomagnetic record of geomagnetic change. And I've just kind of given a few different types. You have the geomagnetic polarity timescale, been incredibly successful, going back hundreds of millions of years, measuring the magnetic reversals and developing an age scale from it. It's developed through time. If you go back, you can actually look at the Hertzler version from 1967, where they just measured deep sea anomaly tracks, and it doesn't change that much from that version, which is pretty amazing. But a lot of the details have come about, and this is just a view of it. It's been incredibly successful. Brad Singer's been sort of pushing this geomagnetic instability timescale. It's tricky. It's a little hard to work with. You have to be careful, but the idea is you would use some of these instabilities in the field, whether it's the Mono Lake Lechamp controversy type thing, and Susan gave us a really nice introduction sort of on that. Didn't really talk about that part, but that's fine. Someday we'll figure that one out. Or some of these other excursions in the record as stratigraphic markers. They're basically times of weak magnetic polarity or intensity where the polarity, well, not the polarity necessarily, but at least the directions go significantly far, more than 45 degrees from the axis of rotation. I would argue that actually even in the Holocene, in certain places there are time intervals that do more than that. So I think we have to be careful on excursions and their use. They're tricky to deal with. There's what I'm calling here the relative paleointensity timescale. And in this case, it's basically the strength of the magnetic field, and that's what Susan was talking about when she was mentioning the paleointensity wiggle matching and for Mono Lake's chronology. This is a version that Jim Channel put together in a stack for 1.5 million years. It's calibrated to the oxygen isotope record, reasonably so, and it's a fairly global. It's mostly a North Atlantic record with a few other sites put in there, but it's a fairly global record, fairly, call it fairly what you want. Here's sort of what we know about that record. If you look at this variation, you see a lot, but you can even look, say, at the last 100,000 years, and higher resolution stacks in black clearly show up more detail than you even get in this blue stack, which shows a lot of variability. So there's a lot of variability in these features which are useful for high resolution stratigraphic control. And in some levels, even in the Holocene. So then that brings us to the Holocene time intervals, and you get this paleosecular variation time scale, as I call it. That's probably a premature thing to call it, but it's based on using variations in declination and inclination and stratigraphically matching them. It has some issues, and we'll talk about how we can improve on that and where Tephra has really come into that work as we move along. So some of the cautionary things that we always have to think about that make things tricky is, first of all, lacking a theory. The paleomagnetic record of geomagnetic change must be learned rather than predicted. Unlike, say, climate and oxygen isotopes, you have this Milankovitch theory. You have this theory of orbital variations inducing climate, which gives you some predictability to the record, and you can use that to understand and get an idea of when you might expect climate variations to occur. Paleomagnetically, we don't have that, right? So we don't know when a reversal is going to occur. We have to learn when the last reversal occurred by accumulation of evidence, datings, and other material. Secular variation, we have no theory to predict when these wiggles are happening or when the intensity is going to go low yet. So because of that, we have to learn these. And that's part of the issue, and that's part of the complexity and why we need Tephra layers to really help us define these things, because they give us, these synchronous lines that we can use, that we can match things if we can tie in where we are. The other thing is the onus is on us to demonstrate that any paleomagnetic record actually reflects geomagnetic change. You have to validate your proxy. You want to make sure you understand that what you're saying is due to a geomagnetic excursion, not somebody putting a fingerprint in the core and they pushed on it, and it's a big disturbance that you measure and causes the magnetic vector to change, because if you're working in soft sediments, they're soft, they're easily deformed. You're trying to do something that's almost impossible when you're working on those, is trying to bring up these magnetic vectors that are aligned with Earth's magnetic field, that are deposited in the sediments. They're probably realigned through bioturbation and other processes, and then you're going to core it, which is a violent process. Then you're going to bring it up to the surface, which is a violent process. Then you're going to split it, which is a violent process. Then you're going to subsample it, which is a violent process. And doing all that, you're going to hope to keep all those little aligned magnetic parameters in there still aligned perfectly and not changed. So, you know, it happens amazingly. I'm always shocked that it actually works. And it works a lot more than it doesn't, but the onus is on us to validate our proxies and prove, or at least come up with a good argument for why you should believe that that paleomagnetic record is actually reflecting geomagnetic change. And therefore, there are lots of magnetic tests that we have to do. And then magnetic acquisition. The age of the magnetization is essentially younger than the age of the sediment, and that is a reflection of the magnetic acquisition process. And older, lower accumulation rate sediments, that can be rather large. So we've been working on this in the Holocene, and we're putting the papers together, but just came out in Sarah Strano's PhD thesis, which she defended. And this just shows some of the North Atlantic records of where we think we know the record pretty well, and then when we compare with radiocarbon dated records, how much temporal offset there can be and how much smoothing of the paleomagnetic record there can be. Actually, it's the smoothing that I was really shocked by more than the temporal offset. Both of them are pretty strong, and these are not low-resolution records. Even the low-resolution records are on the order of 10 or 15 centimeters per thousand years. This one that we're getting our record from is on the order of 2 meters per thousand years. So we're going to kind of jump to those records, because those, I think, tell us about what the geomagnetic field is actually doing and how we can use it. Then Tephras can come in, don't really get into that, but tell us about isosynchronous lines and how another paleomagnetic record may be offset relative to what the geomagnetic field is doing, and we can start to sort these details out. Because, of course, the devil is in the details, and if you don't bring in multiple techniques, you're never going to really get to any of those. Okay, so this brings us to another part of stratigraphy, and something I'm working on, and we can talk about that might be helpful for Mono Lake and some other things, and kind of what I'm calling dynamic stratigraphy. And it's basically trying to get at what's driving geomagnetic change, and can we use the actual changes of the magnetic field and potentially even develop some sort of theory for why these changes might be occurring, where they're occurring, to come up with magnetic stratigraphy. And this is basically comparing modes of behavior and the structure of the geomagnetic field. And these are time average records. And what you see, if you average historically, which is 400 years from a magnetic perspective, you get intensity peaks in certain locations that just don't go away. Sort of implies that the mantle may be influencing the geomagnetic field and providing boundary conditions that influence how that works. If you average over a longer time scale, say the late Holocene here, you get a different pattern. Now the key thing here is this one shows this flux over North America that kind of goes away. This other shows this flux feature over Europe that is really not here in this record. And a lot of things appear to be the oscillation between these sort of modes as it's not just that, but a partial driver secular variation, which allows us to do things to look at records in the North Atlantic and compare them, say, in declination here with intensity in Europe and with intensity, the opposite of intensity in North America, even better inclination here in North America using Western U.S. volcanics, or a stack we've been producing from the Eastern Pacific, from Alaska to Hawaii, and some other records. And you can see that there is a relationship between these. And we're trying to sort out the details between these and really see if we can come up with this dynamic stratigraphy to use maybe our best record from a far-flung place to really predict what the magnetic field might be in some place like the Western U.S., maybe even Mono Lake if we happen to be lucky and it's actually persistent. Okay. So some of our best records have come, and Tephras have been really helpful in them, and they've come from a couple records, one off East Greenland here and one off North Iceland, working with Ann Jennings. And these are really high-resolution records. They're 1 to 2 meters per thousand years, actually 2.322, and the lower part is more like 4 meters per thousand years. Exceedingly high sedimentation rate, so lock-in issues are minimal, decadal probably. So what we did is we stacked things magnetically on PSV. That allowed us to really combined the C14 dates from both records, which interwove exceedingly well, much better than I would have ever imagined before I started the process. They occurred very well. And they also, because in this North Icelandic record, we had a great Tephra record that we compare with. This is Greta Kirsten's daughter's work, and she outlined all these tephras which we had in that record, and we could predict where they might be found eventually in 2322. Initially, the only one that was found in both was the Saxon-Avaten tephra, which was a large eruption, and it's the only one actually in these in 2269 that is actually a layer. All the other ones are cryptotephras, so they take a bit of work to be found. But that sort of laid this out, and we started getting this great record. We used it a little further. We've developed a composite by sort of stacking, and where we don't have overlap, then using the best record. We've been able to compare it with predictions from archaeomagnetic data that sort of suggest that we're right, at least in terms of chronology. We've also used the tephras and their terrestrial dates to try to correct for reservoir age problems with the C14. That's another great use of these things. We should do this right and redo it. Right now I'm just adjusting the age based on a fit to these terrestrial dates here, and that adjusted the old age model about 150 years. Not a huge amount, but it is actually important, and we do see the offsets in the Paleomagnetic record if we don't do it. Okay, so we got these records. They sort of work really well. We got really accurate chronology, put all this stuff together. We have tephras, high resolution, homogeneous. Now we sort of started looking at these things and comparing it with terrestrial records on Iceland from several lakes, and you can map in some of the tephras here, and this is Sædís Ólafsdóttir's paper, part of her paper in geology. I think I have a better figure. Yeah, this is a better figure of this, showing these two lakes that she worked on for her PhD thesis and how that compares with this North Icelandic record. Basically using declination, which we found in Iceland is the big signal there. It's actually, it's huge, it's bigger than I thought, and it's reliably reproducible of hundreds of degrees of declination change in Iceland. This feature actually is excursional right there if you plot it up, because you get about almost 50 degrees of deviation from a pole, and it's only at 2,500 years ago. So I think there's a lot of things in the geomagnetic field we've just been unaware of, because the sediment process, the recording process, really tries to remove a lot of it. It's a low-pass filtered process. So these alignments work pretty good, and these are tephra layers too, these dark ones, that were used as fixed points to help with the alignment. Then there was a lot of little wiggle matching in between to try to make things work and the chronology work out. But we've used the tephras to really help constrain things. Couldn't do it without it. We've also gone with the tephras, and this is a comparison now in depth, and this is a paper coming out in a special issue of the Geological Society that Ann Jennings was leading, and comparing the secular variation from those two cores. We had the tephra in 2269, but we didn't have them in 2322. So Ann used where she thought, where the Paleomag would tell you to look, and she went in with a microscope and started looking for cryptotephras and beginning to find those and beginning to make matches between the two records. This one here is sort of matching out. The big ones are how many, for example, different eruptions there are around the Saxon-Avaten, the different events, and the care you must take when you're in that time interval because of the number of eruptions and the direction you are relative to Iceland, whether you are looking at the same event or another one. Of course, this name for this event comes from the Faroes Island, which is in the other direction, and it may be that this event, which is found in the ice core, and the one in the Faroes, which is in the other direction, might not be the same one, because there are a number of eruptions and events that are found. There's about 5 or 6 of them, and it's more detailed in the paper, but that are found in that time interval. So, you know, care has got to be taken on these things. But, you know, TV 5 seems to correlate with this other Katla eruption, and H3 is also seen to be found in these, as well as the settlement tephra that Ann found in the Greenland core. So there's a lot more details in this that can be worked out. And of course, you know, devil's in the detail, a lot of work needs. This is just showing some of the more comparison of the data that she found looking at both silicic and mafic materials in 2322, and this is sort of the predictions of where things would be based on the paleomagnetic correlation 2269. So we could use that as a way, and it kept her from not looking at every centimeter of a 25-meter core, but some tens or hundreds of centimeters, and actually finding where these are. Okay, so that's the Icelandic part of this story, and it's just one sort of case study. Now I'm going to jump into some recent work we've been doing in Fish Lake, Oregon, on Steens Mountain. I just brought this up as a change, but it does show one thing. The magnetic field goes all over the world, and like Tephra, is applicable both in marine and terrestrial settings. You're not stuck on one or the other. You can use them both places, which you can't with everything. Okay, so Fish Lake in Oregon, nice lake up on the Steens Mountain, beautiful place if you haven't been there. This is a Google Earth shot, kind of rotated around. Fish Lake is over here in Harney County and southeast. We went and recorded that a few years ago. There's a nice campground here, another nicer camping spot over here if you like, and there's a big moraine off the end. It's a moraine dammed lake. The original paleomag work was done by Verisub in the mid-'80s. And Winiger did the original coring in the late 70s on this. So we decided to go back and recore it last summer. We used the UviTech sort of coring system. We got nice multiple cores. Just to show, this was the coring platform on a cataract out there in the middle. Here's a good shot of the moraine that dams it up. A lot of the sediment is basically reworked material off that moraine, making it, you're in a big pile of basalt. Steens Mountain is a big pile of basalt, good for magnetics. It's really nice. So what we did is we were in the field. We measured magnetic susceptibility in the field on cores to help us get our stratigraphic overlap. Here's another picture of it, and this was our field-based magnetic susceptibility records that help us make coring decision and make sure we got overlap of the records to align things. You can clearly see a few spikes that pop out. These, of course, are Tephra, but not all the Tephra show up in the magnetic susceptibility record, but a few do. This is Mazama here, this lower one here. And this is one of the diamond crater events, basaltic events, I believe. But you can see the great overlap we got from the field record. I was amazed this worked out so well, just sitting there by the campsite. I am drinking a beer, of course, telling people what to do, which is the great thing of not being on a boat. We're often work. This is very nice. Okay, we also did things like CT scans on these to look at them, and here's our recovery. Here in CT scans, we found out how well laminated these sediments were. Didn't really realize that. This is just a blow-up of, in here, the Mazama and Toshiwara Tephras that really showed up quite nicely in 3 different cores, as well as several other ones. I don't know if you can see. Most of these little light, high-density layers are Tephra in the record. We're still working out the details of these things, but they're going to be extremely important for us understanding this. These are where the Tephra fit with our C14 chronology initially in the record, including Mazama and its age, using the age from Danauskowitz. Somebody can help me with that pronunciation, please. 1999 from when the Greenland ice core ages for this, and it fits pretty well with our C14 chronology. But when we compare our record, for example, with other records, which I think are pretty robust, and in this case, this is Hagstrom and Champion's Western U.S. volcanics, and what we haven't done yet is pull out which of these are actually dated events and which ones are assumed age events in this record. But you can see there's a lot of similarity, but our ages are a bit older. And one of the things I'm hoping to do is see if we can compare which of these eruptive events here are associated with which Tephra, at least I would hope to see where we are to better align our records and see, because I think we got 2 things going on. Our offset to older ages are due to, 1, reservoir age in the C14. We are looking at bug fat parts primarily, other terrestrial material, so we wouldn't expect a lot of reservoir, but there could be. The other thing is there may be a lock-in effect of the paleomag record, and that's quite plausible. It's pretty soft at the top. you know, sediments really don't lock in right at the surface. They're going to lock in when they, most likely their pore spaces are cut off enough where that's the last time they can unlock. And if the magnetic field's changing, you know, you're going to see that. So that may explain this, and I'd really love to know some of the ages. We have some data and some determinations on these, but, you know, what the actual ages are of these so we can correct and say what's a radiocarbon problem and what is a what we call PDRM, post-depositional remnant magnetization problem in the Tephra records. But there's some really cool dynamics, and that's going to help us out eventually as we do, like I was showing you about the dynamic stratigraphy, when we start comparing these records. Because I think, you know, you can see that there's some temporal offsets, but this is European intensity, which we found that declination really is strongly tied to European intensity in the North Atlantic. So we're all the way in the North Atlantic over here. We see highs in European intensity, declination in the Atlantic moves eastward. Basically, it's pulled that way. Intensities in these spots, it pulls in that direction. We get this strong coupling between those events. That also relates to inclination. It appears in North America. We have this sort of relationship. We need to work out the chronology a bit, but this dynamic stratigraphy looks promising. And I was really amazed because this part of the record, the Verisub chronology is not so good in here, and it's a little bit messy. And this part of the record really comes out extremely well in our new cores. And really shows that this may be plausible. Now we're taking this back. We can use Verisub's older record, they got a little deeper than us, to go back about 14,000 years. But we're working on older sediments. We're going to try to tie this in, and our hope is to go even farther back. So this is a little case studies. I'd love to go off the west coast of, you know, in the Pacific and start doing some more of this, deeper times. There's nothing that says you have to use the Holocene to do this kind of thing. We can just test it then, and we can define it as a method then. Then hopefully we can push it back in time and employ it. And Tephra layers are going to be very important to really making these kind of things work. So just some opportunities quickly. We're beginning to recognize what appears to be fundamental modes of paleomagnetic behavior, semi-secular variation, that have a lot of stratigraphic opportunity. The key to testing these really initially is developing well-constrained, accurate, independent chronologies, and that's what we've been trying to do on all our records, not wiggle matching the paleomag, but actually testing the relationships that are observed with well-constrained chronologies to understand what's going on, that then we might use as a better stratigraphic tool because we understand the dynamics behind it and can apply it deeper. Tephras provide critical tool for the stratigraphic alignment, both locally, marine, terrestrial. Hopefully, Paleomag can also help assess which tephra you might be looking at, especially in cases where you have, say, a center giving you multiple eruptions that may be going in different directions that, you know, if you have really good paleomagnetic records, you can define which one is which, and that kind of gets the force. So that's it, and thank you. Cheers. Questions?
Was Fish Lake formed by people here at some point? Or
Yeah, originally.
Okay.
Yeah, in 70 some odd.
And was he able to identify all the tephra layers there? And
They are the same tephras that were in there. They weren't originally identified. They were just numbered, and right now I've kept the same numbering. But they've been working on it at Washington State a bit more through the time. I think there's a paper, I don't know, it's been 40 years in the works now, that hopefully is going to come out with some more identification on some of these events. So we've looked a little bit at the chemistry of these, have some basic ideas of which ones are which, but we haven't gone through the details. Yeah.
I'm curious, in your Fish Lake record, why you chose to use an age for the Mazama eruption that was based on an ice core time scale. You said you used a GIST age? I might have
Yeah. It was, well, actually, I read to the north. That seems to be very consistent with from what I understand, and I'm sure somebody, you know, might know better, but very consistent also with local radiocarbon dates. It just seems to be one that people type, I don't know, somebody else might know. Give me some other reasons. It seems to be a good age for it.
there's a summary paper that came out some years ago,
Right.
in the Canadian journal. calibrated 7,600 something.
Okay. Which
That
is
is an average of all sorts of ages, but the best. What do you have there?
7627
Yeah.
plus or minus
About.
150, so it's
The author there is Canadian.
Huh?
The author there is Canadian, so it's got
Yeah, it's right.
There you go.
that's tied in with their radiometric gauges as well, so that was reasonably robust. Yeah, and then they gotta nail it. But it's nice having those paired eruptions so you can see in the lakes to the south, and you compare secular variation patterns to around there. And if you compare those, say, with the erupted products and the actual volcanic records and look at what you're detonating there versus your jet sediments, it should line up. We haven't done that yet, but I think that would be a nice way of rounding this all together. Yes?
Non-Tephra related question.
Oh, thank you.
Have you compared your paleomagnetic events with the calibration curve, radiocarbon calibration curve, to see if any of the events are coinciding with changes in radiocarbon?
Yeah, have been, and I've been looking at that in a lot of different ways. Nothing really, no traction exactly yet, but I put that together all the time. I do think that some of the bigger events in radiocarbon happen to be during times of shifting from, say, one flux load, one mode to the other. And during those times, in between that, the field appears to get weak for a short period of time. At least in the North Atlantic it does, and some other areas. And I've looked at North Atlantic, actually, some inclination. There is a geomagnetic, I think, explanation to a lot of the radiocarbon variations, even the high frequency ones. But I think it's a complex explanation, not a simple one-to-one explanation, and therefore it's not really come forward. It's easier to call on solar variability. But happy to show you data. Yes, I've spent a lot of time looking at things.
So you have something around about 2,500?
Yes, right, and that actually occurs with the younger of those big C14 anomalies. That the older one actually shows up with some variations we have in some Arctic records that suggest that the geomagnetic field is going in. But it's nothing consistent. So I'm waiting to get enough data until we can put a really consistent argument forward and something that's somewhat convincing rather than just saying it and make it unconvincing. Because the geomagnetic field, the key thing with geomagnetic field is a very local effect. Every local record you get is it's kind of a local picture on a global process. So everything has local dynamics, and there are local dynamics in it. So, for example, you're not going to expect to find the same exact signature between, say, a record of an excursion that you measure or something in the North Atlantic with one you find, say, at Mono Lake. They're going to have some different dynamical features associated with them. So you got to find the same way of comparing those two things, which make it tough. Or, for example, the South Atlantic anomaly. Most of our intensity loss presently is really due to one location's really deep drop in intensity. If you could have data from most of the world and not have data from that location, you wouldn't know that the intensity is actually dropping to the same degree. So a single location can have a big effect on the global field and on the shield and for C14, which makes it tricky.